Hey there, my name is Nazzal Naseer, and in this video I'll talk about how I wrote my own rendering engine which uses the ray tracing technique. Before we get into the meat of the project, let me talk briefly about what rendering actually is. Simply put, rendering is the process of generating images. If you've used a design software like AutoCAD or Blender before, or if you have experience in visual effects, you'll know that rendering engines are used to produce the final result. But most rendering engines today use the rasterization technique to render images. You see, in rasterization, objects in a scene are composed of tiny little polygons. Rasterization computes the position of the edges of these polygons that exist in a 3D space to find their corresponding positions on a 2D space, which is your screen. The problem with this approach, however, is evident in the realism of the rendered images, or the lack thereof, because rasterization does not take into account the behavior of light, and therefore has a trade-off when it comes to accurately computing depth, shadows, and so on and so forth. What does take the behavior of light into account is ray tracing. Ray tracing shoots a ray from the viewpoint to each pixel of the image and traces the path till it eventually bounces off to a source of light, like how real life works, except in reverse. As it traces the path of the ray, it's also collecting information on the objects that the ray is coming in contact with. This takes care of shadows, depth perception, and everything else in just one step. And because this process emulates the behavior of light, the rendered images are very realistic. This is how I went about writing the program. As you can probably tell, I've used the object-oriented programming methodology to write my code. Every component of the project is introduced as an object of a class here in this main function. There's a camera object, a source of light, a sphere, the properties of the sphere, the position of the sphere, an object that defines the scene, and an engine that's supposed to render the scene. Going with this approach definitely helped make the entire implementation process intuitive. In fact, the first function I defined in this project was the main function, and each class was defined subsequently. For example, after I decided that I wanted a sphere in my scene, I instantiated a sphere object with radius and position. And only after doing this did I define the actual sphere class. Every object of this class will have radius, a position, and some material properties. And because we need to know what a source of light comes in contact with in the scene, we define a hit-by-light function that returns the distance between the source of light and the sphere object. I was easily able to find the sphere-ray intersection formula by simply Googling it, and the math isn't too complicated. And that's the beauty of this project, is that it allows engineering students like me to put concepts like rays, vector manipulation, transformation functions, and more into direct practice. The math formulas are direct, and none of the math operations go beyond the scope of what we've already been introduced to. I've linked to all the resources you need to understand the math behind this project in my GitHub repo. I plan to continue working on this project so that I can make the rendering itself faster, and also introduce other objects such as a plane and a cube. Working on this project helped me understand the strengths and weaknesses of MATLAB. Thank you.